On May 8, 1945, the operational lifespan of a Republic P-47D Thunderbolt known as Dottie Mae reached an irreversible threshold. Bearing Army Air Force's serial number 4-2-29150, this heavy fighter survived around 90 combat missions across the European theater. On the final day of the conflict, the flight profile called for a morale-boosting aerial demonstration over the recently liberated Ebensee concentration camp, a sub-camp of Mauthausen. Instead of returning to base, the aircraft vanished beneath the surface of an Austrian lake. It settled inverted in deep silt. The objective decades later was to locate and extract this exact airframe from deep water. Plucking a heavy aluminum machine from a flooded environment without breaking its spine requires precise forensic handling. Before its sudden disappearance, this specific Thunderbolt operated as a highly utilized ground attack platform. Completing roughly 90 combat sorties subjected the airframe to extreme structural fatigue before it ever touched the water. When it finally came to rest at the bottom of Lake Traunsee, it transitioned instantly from a military asset into a submerged archaeological site. For decades, the precise coordinates of the wreck were never formally recorded or verified by a documented survey. During this prolonged operational gap, the aircraft rested completely isolated from surface intervention. The environment at 210 feet is dark and near freezing. The Thunderbolt lay motionless on the lake floor. The immense weight of its radial engine and armor plating drove the nose and upper fuselage deep into the soft lakebed sediment. That burial did more than hide the wreck. In cold mud, time slows and decay can stall. For 6 decades, the silt held the story in place. In the early 2000s, an Austrian recovery firm named Sandy Air Corp initiated a formal operation to close this historical gap. Finding a single submerged fighter aircraft in a massive alpine lake requires a rigorous systematic discipline. At the lakebed, diver bottom time was measured in minutes, and blind exploration was impractical. The team needed instruments, not eyesight. The search teams had to approach the water column as a blind geometric grid. For 2 years, the firm systematically scanned the deep basin. The objective was to isolate a dense metallic return against a background of natural geologic clutter. The prolonged duration of this search phase illustrates the inherent difficulty of locating an aircraft that has been entirely swallowed by the local topography. The silt layer that protected the airframe from rapid oxidation also served to camouflage its acoustic and visual signature. When the survey teams finally verified the target location, the recovery operation immediately shifted from a search mission to a structural assessment. Confirming that the target was indeed the missing Thunderbolt was only the preliminary requirement. The recovery engineers now faced a rigid set of physical constraints. The aircraft was confirmed to be structurally continuous, but it was heavily embedded in the mud. Resting inverted at 210 feet meant that the belly of the aircraft faced the surface, while the most historically significant elements remained trapped under the mudline. Any future extraction plan would have to account for the massive suction forces exerted by the deep sediment. Engineers had to carefully evaluate whether the baseline aluminum structure could survive the dynamic loads of a vertical hoist. Flooded cavities and trapped sediment meant the true load could not be guessed from the surface, even with the protective benefits of the deep silt. 60 years of submersion alters the tensile strength of aviation fasteners and wing spars. The teams had to measure the risk of the heavy tail section snapping under the sheer strain of its own water weight. How does a heavy combat fighter survive 6 decades under 210 feet of water without surrendering its structural integrity to rapid corrosion? That final morning, the low-level flight profile around the Austrian lake compressed into a severe operational hazard. In mountainous terrain, a fast pass over flat water leaves little margin for vertical error. Pilot Henry Moore descended below the primary flight group to maintain constant visual reference with the surrounding terrain. A momentary dip in altitude caused the sweeping arc of the propeller blades to clip the surface of the lake. The instant the spinning metal blades penetrated the water, the aerodynamic stability of the aircraft shattered. The immediate consequence of this physical contact was hydrodynamic drag transfer. When the rapidly spinning propeller blades sliced into the lake, the water acted as a dense physical brake against the propulsion system. This kinetic energy stripping violently transferred the rotational momentum of the massive radial engine directly into the unyielding fluid. The tremendous drag mathematically prevented the power plant from maintaining the revolutions required to sustain forward flight speed. Deprived of essential thrust, the heavy fighter suffered an immediate and irreversible loss of aerodynamic lift. Moore faced a forced emergency splashdown with zero altitude available for recovery maneuvers. Ditching an aircraft of this size involves tightly managing forward momentum and descent rate to prevent total structural disintegration upon impact. The pilot had to keep the nose elevated as the fighter decelerated rapidly just above the waves. When the lower fuselage finally struck the lake, the water forcefully resisted the forward motion. The sheer violence of this deceleration event focused extreme hydraulic pressure against the deployed control surfaces. The immense drag forces acting on the underside of the wings far exceeded what the aircraft was designed to absorb in water impact. Control surfaces and lower structures suffered severe damage. Despite this, the heavy central tub of the fuselage managed to withstand the shock loads. The robust wartime engineering of the cockpit cage and the heavy reinforced engine mounts helped prevent the forward section from crushing inward under the pressure. Because the primary structure held together, Moore was able to successfully evacuate the cockpit before the cabin entirely flooded. Local civilians operating a nearby rowboat navigated out to the crash site and pulled the pilot safely from the freezing water, reportedly 2 young women and a young man. The human element of the ditching concluded without a casualty, but the physical journey of the Thunderbolt was only just beginning. As the pilot climbed into the rowboat, the flooded airframe rapidly lost its remaining residual buoyancy. The structural weight of a P-47 is heavily biased toward the front due to the immense mass of the double-row radial engine and the forward armor bulkheads. This extreme forward center of gravity strictly dictated the sinking mechanics of the heavy fighter. As the aircraft slipped beneath the surface, the engine mass pulled the nose vertically downward into the dark water. Passing through the water column, the massive surface area of the broad wings interacted with the fluid dynamics of the descent. The rushing water pressure pushing against the asymmetrical aerodynamic shapes induced a powerful rotational force on the sinking mass. The airframe rolled completely over during its rapid fall toward the lake bed. The descent violently halted when the forward momentum drove the engine cowling the propeller hub and the upper fuselage deep into the soft sediment at the bottom of the lake. The kinetic energy of the crash and the subsequent freefall anchored the Thunderbolt perfectly upside down in the cold mud. With the radial engine pinning it in place, the P-47 settled into a mud layer that sealed the evidence where it fell. Human eyes and conventional optical cameras cannot penetrate the pitch-black water at a depth of 210 feet. Locating an airframe buried in an alpine lake requires overcoming severe sensor limits. The resting place of the Thunderbolt lay precisely 600 feet from the eastern shore of Lake Traunsee. At this depth, sunlight fails entirely and suspended glacial sediments scatter artificial diver lights, rendering visual navigation useless. To find a submerged aluminum structure, operators had to abandon optical searches and rely strictly on acoustic geometry. For 2 years, Sandy Air Corp dragged sensors through the basin, logging every pass until the coverage was complete. In April 2005, the search team successfully mapped the location of the wreck using a side-scan sonar system. This procedure relies on a mechanical principle known as acoustic shadow targeting. The sonar towfish transmits high-frequency sound pulses laterally across the lake bed rather than looking straight down. When the acoustic wave strikes a solid mass like an inverted fighter fuselage, the sound energy reflects back to the receiver. More importantly, the object blocks the sound waves from traveling further, casting an acoustic shadow across the topography behind it. By analyzing the shape of this return in shadow, operators can infer the wreck's outline, orientation, and the way it sits in the silt without ever seeing it. The sonar returns indicated a large, intact structure resting upside down in the deep silt where the acoustic shadow pointed. Deploying remotely operated vehicles to visually inspect the acoustic target revealed a startling level of physical preservation. The initial camera passes proved that the aircraft had not shattered upon impact but had settled as a continuous structural unit. The inverted resting position meant that the most iconic and delicate sections of the forward fuselage were driven violently into the lakebed sediment. This deep burial triggered a chemical preservation mechanism defined as anaerobic mud sealing. The heavy compact sediment surrounding the cockpit and engine cowling completely isolated the aviation aluminum from the surrounding water column. By depriving the submerged metal of the dissolved oxygen required to fuel catastrophic galvanic corrosion, the mud effectively halted the decay cycle. The lack of oxygen in this deep sediment envelope kept the structural skin, thin-gauge aluminum panels, and internal wing spars remarkably sound. The effectiveness of this low oxygen preservation was strongly suggested by the condition of the exterior paint. As the remote cameras hovered near the buried forward section, they captured a visual signature that confirmed the identity of the aircraft. The original wartime nose art remained legible on the left engine cowling. Painted by ground crew, the artwork featured a Vargas calendar-style pin, up commonly titled Santa's Little Helper. Because this section of the cowling was encased in dense sediment, the delicate pigments and lettering survived decades of submersion far better than exposed surfaces. This preservation of the painted name Dottie Mae served as a key anchor for identification. While the exposed belly of the aircraft showed signs of interaction with the water, the vital components locked in the silt remained pristine. The acoustic search successfully located the Thunderbolt, and the environmental conditions preserved its forensic integrity. The survey confirmed the physical dimensions and structural continuity necessary to plan an extraction. Mapping the site was not recovery. The remote survey introduced a non-negotiable constraint: the possible presence of wartime weapons and ammunition still associated with the wings. A military wreck is never treated as a neutral object under that suspicion, so the site became a controlled hazard zone, documented, assessed by qualified specialists, and cleared under the responsible authorities before any rigging plan could be approved. And even then, the mechanical reality remained unchanged. The central fuselage was still locked into the lakebed, embedded in dense sediment that had held it for decades. The heavy radial engine and the flooded cockpit still anchored the aircraft to the bottom of the lake. The salvage team now faced the immense reality of moving the fragile artifact from the lakebed to the surface. How do engineers safely rig and hoist a massive inverted structure filled with water without breaking its fragile spine? On June 13, 2005, the recovery operation reached a critical trade-off edge. The hazard mitigation cleared the strict legal boundary for the lift, but the engineering reality of the extraction remained highly precarious. Resting inverted at a depth of 210 feet, the flooded Thunderbolt presented a severe mechanical puzzle. The salvage team had to execute a surface crane hoist without tearing the fragile aluminum structure apart under its own water weight. The core procedural problem was the massive volume of fluid trapped inside the fuselage and the partially sealed wing sections. While fully submerged, the aircraft benefits from the natural buoyancy of the displaced water. However, the moment the airframe breaks the surface, the internal fluid instantly transforms into immense dead weight, pressing directly downward against the canopy rails and upper fuselage panels. This dynamic creates a severe structural challenge defined as inverted lift geometry. Combat aircraft are specifically engineered to carry heavy structural loads through the landing gear mounts and lower wing spars while resting right side up. They are not designed to be suspended upside down by cables. When a heavy combat airframe is hoisted in an inverted orientation, the lifting straps apply intense crushing forces to the weakest upper sections of the fuselage skin. If the load distribution was wrong, the tail would behave like an unbraced lever, concentrating stress at the cockpit bulkhead during the ascent. To counteract this specific structural vulnerability, the deep water divers meticulously routed wide synthetic lifting straps around the strongest surviving structural members of the inverted fighter. By cradling the load across primary load paths, the rigging plan distributed the inverted water weight away from the most delicate upper aluminum skin. With the sling securely locked into position, the surface crane operator initiated the highly controlled vertical ascent from the lakebed. The initial cable tension had to overcome the intense suction force of the deep alpine mud that had firmly gripped the engine cowling. The crane applied steady upward pressure until the sheer mechanical force finally broke the vacuum hold of the silt. Once the heavy engine block pulled free from the bottom, the Thunderbolt began its vertical journey through the cold water column. The hoist was deliberately paced at a crawl to prevent the heavy airframe from swinging like a pendulum beneath the surface vessel. The crane operator paused the lift at regular depth intervals. This disciplined pacing allowed trapped lakebed sediment and dense mud to slowly wash out from the open gear wells and the trailing wing edges where the flaps had been torn away during the original water impact. The maximum dynamic stress on the airframe occurred at the exact moment the metal breached the surface of Lake Traunsee. As the buoyant support of the surrounding water fell away, the full atmospheric weight of the flooded structure transferred entirely onto the synthetic lifting straps. The crane operator held the fighter suspended just above the waterline, allowing heavy volumes of fluid to cascade out of the tail cone and open wing roots. This controlled draining sequence safely reduced the overall mass of the suspended load. Only after the water weight was mitigated did the crane carefully swing the heavy artifact over the waiting recovery barge. The meticulous rigging strategy held the primary structure completely intact throughout the dynamic hoist. The heavy fighter was carefully lowered onto a custom floating dock precisely as planned. The extraction phase concluded with total structural success without inducing any new deformation to the historic metal. The airframe was successfully transferred to a floating dock, but pulling it from the anaerobic deep triggered an immediate countdown for preservation. The engineering threshold for resurrecting a submerged combat aircraft is often judged by how much original structure can be conserved and safely reused. In this case, restoration accounts have reported that roughly 50 to 55% of the recovered airframe was retained as original material. If too much of the original aluminum must be discarded, a project risks becoming a modern rebuild centered on a vintage data plate rather than a conserved artifact. When evaluating a recovered airframe, inspectors focus on which original components can safely bear modern loads and which must be replaced with newly fabricated parts that match original specifications. The goal is to preserve identity through documented conservation choices, not by chasing a rigid formula. Reaching that retention threshold required immense technical discipline from the rebuild team. The original Vargas calendar nose art that confirmed the identity of the aircraft was carefully stabilized by conservation experts. The restoration engineers successfully grafted these original painted cowling panels back onto the reconstructed forward fuselage. Mating 60-year-old stressed metal with perfectly aligned new aluminum structure requires extreme dimensional precision. Wartime manufacturing tolerances often varied widely from the original engineering blueprints, meaning the modern team had to reverse engineer specific assemblies to ensure the heavy fighter would perform under extreme stress. They also had to carefully insulate the joints where original wartime aluminum met newly fabricated metal to prevent any future galvanic corrosion between slightly different alloy batches. The meticulous restoration demanded thousands of hours of disciplined labor to clean, inspect, and treat every surviving rivet hole and structural bracket. The massive double-row radial engine was entirely overhauled, with mechanics salvaging whatever original internal heavy steel components still met strict aviation safety tolerances. Every hydraulic line, electrical bundle, and flight control cable had to be entirely replaced to satisfy modern airworthiness directives. But the core structural identity of the Thunderbolt remained intact. The central cockpit tub, the heavy pilot armor plating, and significant portions of the original wing structures were seamlessly blended with the new material. By the end of the 12-year project, the physical remnants of the sunken fighter had been completely transformed back into an active flight vehicle. In late June 2017, the heavy fighter successfully completed its first post-restoration test flight, with sources variously placing the date on June 22nd or June 23rd. The operation to locate, recover, and meticulously rebuild Dottie Mae proved that even an aircraft subjected to severe ditching forces and 6 decades of submersion could be structurally reclaimed. When more than half the original machine takes to the sky again, flying as it did in 1945, that becomes the measure of recovery.